So if my if my change in distance is 120 millimeters, and my total time is 15 millimeters, then my delta D, my change in distance over my change in time, is going to equal 120 millimeters over 15 minutes. That will be equal to, it's going to be 8 millimeters per minute. Okay, so that's my rate of diffusion. So the dye diffuses at a rate of 8 millimeters per minute. All right, in just my example. Now, of course, there's no real dye, there's no real auger, and of course this is movie magic, so you can't trust anything I say. All right, so defining osmosis. Remembering that osmosis is the passive movement of water from an area of high concentration to area of low concentration, psi. All right, so cells, this is going to occur through a plasma membrane. All right, let's do some more math. Again, with the math. Always with the math. Thought I just did math. So water potential is the concentration of water, as we discussed before. That's water potential overall. That is actually equal to pressure potential, psi p, plus solute potential, psi s. Now, solute potential is always going to be a negative number. It's always going to be negative. It's always going to be a negative number. Now, when psi is equal on both sides, we're going to call that equilibrium. That's psi equals 0. Water is going to water is always going to be moving to reach equilibrium. So we're always going to go from an area of high water potential to an area of low water potential. But let's take a look at what's going to happen here. Let's see how this is affected. Pure water has a water potential of 0. It has no solute. So the solute concentration in pure water, pure H2O, is going to have a water potential of 0 because we're not going to put any pressure on this water and there is no solute in it. So because there is no solute in this water, there is no solute potential. And because we're not putting any pressure on this water, there's no pressure on it. So there is no water potential. So distilled water under no pressure is 0 water potential. Now, let's say that we have pure water on this side. So we have pure water versus an increased solute concentration. An increased solute concentration gives us a negative solute potential that will lower our water potential. And decreased solute potential will raise this number and give us a higher water potential. So, I'm going to erase that so everything's nice and clean. Pure water versus high solute. We have no pressure plus negative solute potential. That means we have 0 versus a negative water potential. Which is higher, 0 or a negative number? 0 is the higher number. Water will move from high water potential, from low water, I take it back. This is the higher water potential. Water will move from high water potential to low water potential, down the water potential gradient from 0 to negative. So, in this U-bend right here, our pure water is going to move across our partially permeable membrane from an area of high water potential to an area of low water potential because of the presence of salt. Our salt is causing water to leave this pure water. Water potential. Water follows salt. Now, let's take a look at how pressure deals with this. So let's discount our solute potential for a moment. We have pure water on both sides. If I apply pressure to this side of the tube, my pressure potential goes up, my water potential goes up. My pressure potential goes down, my water potential goes down. If I blow into the tube, my pressure goes up. If I suck on the tube, the pressure goes down. Now, of course, it doesn't seem very productive because this is an electronic board and I'm not going to do that. So, all right. Now, this being zero water potential over here, this is going to be a positive water potential, greater than zero. This having negative pressure will have a negative water potential. Water will move from the high water potential, a now positive, to the low water potential, still zero. Down its water potential gradient to cross a partially permeable membrane. Here, water will move across the partially permeable membrane by osmosis from high water potential, 0, to low water potential, negative. Now, how would we get pressure in a cell? Who is squeezing my cells? Well, the cell is squeezing my cell. If I have a plant cell, I have this interesting little thing called Newton's laws of motion, where I have every action has an equal and opposite reaction. If I am having water drawn into the cell following salt, then that means that water is going to go somewhere. That water is going to take up space. That cell is going to swell. So when that cell swells, the water taking up space is going to put pressure on the cell wall. The cell wall, being a stiff cellulose structure, is going to exert pressure right back on that water. So, every action has an equal and opposite reaction. Pressure being exerted on the cell wall, the wall is going to exert pressure equally and oppositely against that water. So this will be an opposed pressure. So the pressure potential exerted by the cell wall will eventually equalize the negative solute potential, and we will eventually obtain equilibrium. Equal forces of pressure and solute potential, opposed forces. Pressure forcing water out, and solute potential drawing water in. And that gives us a stable system of equilibrium of 0 water potential, water coming in and out at the same rate. So, let's pause the video.